Good morning, students of grade 8 and 9 of Kumudini Secondary School. Today we are going to continue our simple machine lesson, lever. Okay, up to our last class we discussed about efficiency and relationship between efficiency, mechanical advantage and velocity ratio. Today we will discuss about lever and numericals related to it. Okay, what do you mean by lever? Lever is simply a rigid bar. Yes, it is a rigid bar, okay, which is fixed at a point called, what do you call the fixed point? You know this, that is called fulcrum. Yes, at a point fulcrum, and can rotate freely about the fulcrum. Okay, so if any structure can be rotated by some point, by keeping it fixed at some point, you can rotate that structure freely, then it is lever. Okay, so suppose this is the point where it is fixed, means this is fulcrum. Yes, so in either side and either point you can keep load in one of the point and you apply effort in another point. Okay, so a lever consists always consists of three parts. Yes, parts of lever. Number one, load. Number two, fulcrum. And number three, effort. Okay, load is the part of lever where the lever performs work, whereas effort is the part of lever where the user performs work. And the distance between load and fulcrum, it is called load arm. Okay, the distance between load and fulcrum, that means here to here, load and fulcrum, this is called load arm. And distance between fulcrum and effort means from fulcrum to effort, this distance is known as effort arm. Okay, and in some cases, especially in books, load arm and effort arm are also defined as, they are also referred as load distance and effort distance. But don't be confused, load arm and load distance are not same. Okay, load arm and load distance, they are not same, neither they are same nor they are equal. And effort arm and effort distance are also not same, neither they are same nor they are equal. However, the ratio of effort arm, okay, ratio of effort arm to load arm is always equal to ratio of effort distance to load distance. Okay, don't forget this. Okay, in a simple machine or in a lever, effort arm and effort distance are not same term. Load arm and load distance are not same term. However, the ratio of effort arm to load arm is always equal to ratio of effort distance to load distance. Okay, that is why when we calculate VR, actually our formula is effort distance by load distance, isn't it? Effort distance by load distance. However, mostly question does not give us any information on effort distance and load distance. Indeed, they give us information on effort arm and load arm. Okay, so since they are proportional, we can replace this by another formula, effort arm by load arm. Okay, that is why many people use them interchangeably, but they are not interchangeable. Okay, individually they are not interchangeable. Okay, you should keep these things in your mind while performing numerical. We'll do that shortly. Okay, for now let's go to types of lever. Types of lever. Okay, based on the position of fulcrum, load and effort, there are three types. They are first class lever, second class lever and third class lever. Okay. First class lever means it has suppose this is a lever, fulcrum is in middle, load is at one side and effort is another side. Okay. And second class lever, it has fulcrum at one of the corner, load is in middle and effort is applied at another point. Yes. And in third class lever, fulcrum is at one side and load is in another side, effort is applied in the middle. See, so this forms a memorizing factors. First class lever has fulcrum in middle, second class lever has load in middle, and third class has effort in middle. Remember this, memorize it. FLE, flee, FLE, flee. F for fulcrum, L for load, E for effort. Okay, now let's go in detail about first class lever. First class lever. Okay, first class lever, as I already told you, it has fulcrum in its middle, load and effort. Okay, there are three distinguished cases of first class lever. In one of the case, load arm, okay, let's write LD, load distance is equals to effort distance. That means fulcrum lies exactly in between load and effort. Okay, one of the kind of first class lever is the lever in which fulcrum lies exactly between load and effort, and such type of example of such type of machine is physical balance or tarazu. Okay, physical balance and seesaw. Seesaw means tiki chow. These are first class lever in which fulcrum lies exactly between load and effort. And what advantages provided by such simple machines? Do they multiply force? No, they do not multiply force. What they do, they change direction of force. Okay, this type of first class lever, they change direction of force. Okay, and secondly, transfers the force from one point to another point. Okay, these two are the advantages provided by first class lever, having fulcrum exactly between load and effort. Okay, and second type of first class lever has fulcrum somewhat closer to load. Okay, that means LD is smaller than ED. In such case, what happens? Let's say according to principle of simple machine, we can say E into L into LD equals to E into ED. Do you remember this? Okay, last time we discussed about it in our previous class. Now by cross multiplying, what you get? L by E is equals to ED by LD. Yes. Now since, look here, LD is less than ED. Here LD is less than ED means value of numerator ED is greater than LD. Numerator is greater than denominator. Then ED by LD, what shall it be? Will it be greater than 1 or less than 1? Always remember, if numerator has greater value, then the fraction will always be greater than 1. For example, let's say 5 by 2, numerator is larger, it gives you 2.5. Or if you write 2 by 5, numerator is smaller, it gives you 0.4. Okay, always remember, if numerator is greater, value is always greater than 1. If denominator is greater, value is always smaller than 1. And if numerator and denominator both are equal, then value is always 1. Okay, so in this case, L by E is equals to ED by LD. Then if ED by LD is greater than 1, it implies that L by E must also be greater than 1. See, this is a simple chain. Okay, L by E is equals to ED by LD. L by E is equals to ED by LD. And if ED by LD is greater than 1, then L by E must also be greater than 1 because they have same value. Yes, that is, it gives us L is greater than effort. See, what you can see, by applying smaller amount of effort, you can lift larger amount of load. It means it shows that larger load can be lifted by applying smaller amount of effort. Got it? So what advantages does it provide to us? First of all, see, you can see your effort is being multiplied. Yes, your effort is being magnified. So it magnifies applied effort. And obviously first class lever always changes direction of force and transfers force from one point to another. To say in this case, you apply force here, it is transferred to here. Okay, you need to copy it, you need to take the note. Okay, you can pause the screen and take it. Okay, first class lever, case number A and case number B and its advantage. Okay, now let's go to case number C. Okay, case number C. Once again we are talking about first class lever, but in this case fulcrum has been shifted toward effort and load is kept here. In case number 3, fulcrum has been shifted toward effort. Okay, so in this case, load distance is greater than effort distance. You have seen such kind of simple machines. Some examples are catapult. You know catapult. Okay, in case of catapult, no. Catapult is in second case, I guess. No, yes, it is so. Okay, in case of catapult, it is very ancient machine. Okay, simple machine in which is used in siege. Okay, so it is kept like this. Here, a large stone is kept, or sometimes this stone is also filled up with explosive. Okay, and here a large heavy load is kept. Okay, and when it is taken downward, the load over here is thrown very far. Okay, in this case, see, effort is applied here, load is here, effort distance is smaller than load distance. Yes, okay, in this case what happens, let's see. Once again, from the principle of simple machine, we are going to determine what advantages are provided by the lever when fulcrum is shifted near the effort. Okay, from principle of simple machine, we are going to repeat the same procedure. L into LD equals to E into ED, just like in number B. Yes, or by cross multiplying you get L by E is equals to ED by LD. Yes. Now since LD is greater than ED, that means here, look here, LD is greater than ED means denominator is greater than numerator. Okay. What happens to the fraction when denominator is greater? As I told you already, when denominator is greater, then the fraction will be less than 1. When denominator is greater, then fraction will be less than 1. It implies if ED by LD is less than 1, then L by E must also be less than 1. Yes, because L by E is equals to ED by LD. It implies L by E must also be 1. Therefore, it gives L is less than E. You can see effort, large amount of effort. More effort is needed to lift smaller amount of load. It shows that a larger amount of effort is needed to lift smaller amount of load. For example, if you need to lift a load of 100 Newton, you might need to apply force of 300 Newton. It does not provide us any mechanical advantages. Okay, then why do we use it? What advantage does it provide when fulcrum is shifted toward effort? As you know, since ED by LD is less than 1, it has less VR as well. That means it makes our work faster. Okay, and since ED by LD is less than 1, its VR is also less than 1. So it makes our work faster. So in this case, in case of this simple machine, time is traded with effort. You need to apply more effort to reduce the time. Okay, you need to apply more effort to reduce the time. And in this case, you need to apply, trade effort with time. Yes, your effort is multiplied, but it consumes more time. Okay, nothing in the world is ever free. Okay, so what advantages are provided by this type of simple machine? Number one, it does not magnify, but it makes our work easier. Makes our work easier. And number two, obviously first class simple machine always changes direction of force. And number three, it transfers the force from one point to another. And this third advantage, it is provided by all kinds of simple machine. Okay, do you understand this or not? The question is what happens when fulcrum is shifted to effort? Okay, what happens when fulcrum is shifted to load? Okay, and previously in this case, what is the question? What is the question in this case? What happens when fulcrum is shifted to load? Okay, these are very common question. What happens when fulcrum is shifted to load? You need to do this much. Okay, and if you are asked what happens when fulcrum is shifted to shifted to effort, then you need to do this much. Okay, now let's go to second class lever. Number 2, second class lever. Okay, second class lever has only one case. Okay, in second class lever, fulcrum lies at one point, one end, and load lies in middle, and effort lies in another point. See, so from here fulcrum to load, it is load arm, also indicated as LD, and from fulcrum to effort, it is effort arm. Okay, in a second class lever, you can see that since load lies in between fulcrum and effort, load distance is always smaller than effort distance. Yes, in a second class lever, LD is always smaller than ED. Okay, now we are going to determine what advantages are provided by second class lever. Okay, once again we are using from the principle of simple machine. We are using principle of simple machine. L into LD equals to E into ED, or L by E is equals to ED by LD. Yes, now since LD is always less than ED, that means which one is greater here among ED and LD? ED is greater, isn't it? That means numerator is greater. And what happens when numerator is greater? Its value is always greater than 1. Okay, when numerator is greater, its value is always greater than 1. Therefore, since L by E and ED by LD are equal, and ED by LD is greater than 1, L by E is also greater than 1. That is, it gives us L is greater than E. See, load is greater than effort. Means, what advantage does it provide? It shows that this is also the case of first class lever with fulcrum closer to load, isn't it? This is the same case. Let me show you here. See, in this case also you got L greater than E. Yes, here also you are getting L greater than E. Shows that larger load can be lifted by applying smaller amount of effort. Okay, and what are the examples of this kind of simple machine? Can it be nutcracker? In nutcracker, knot is kept in between, fulcrum is there, and you apply effort here, isn't it? Find other examples as well. I am giving you only one. Now you can write what are the advantages provided by second class lever, can't you? Advantages. Number 1, I'm going to write in short. Okay, you write in full sentence. Magnification, magnifies effort. Okay. Number 2, does it change direction? Does it change direction? No. If you apply force downward, then load also moves downward. If you apply force upward, then load also moves upward. It does not change direction, but what it does, it transfers force from one point to another. Okay, this one. Let's go to okay, you need to copy this. Pause the screen. Copy it. Huh? Okay, let's go to third case, that is third class lever. Okay, number 3, third class lever. In third class lever, fulcrum is here and load is kept in another end. Effort is applied in between. Okay, so from fulcrum to effort, it is effort distance, ED, or effort arm, sorry, and from fulcrum to load, it is load arm, LD. Okay, third class lever. Now it shows that in a third class lever, since effort is always in between load and fulcrum, ED is always smaller than LD. Yes, ED is always smaller than LD. Then what happens? Let's see. Once again, we are going to follow the same steps according to principle of simple machine. By now you must have the graph of this derivation. L into LD equals to E into ED, or L by E equals to ED by LD. And since ED is always smaller than LDC, ED is always smaller than LD, means numerator is smaller than denominator, then ED by LD is also less than 1. Therefore, L by E is also less than 1. That is, it provides us L is smaller than E. Okay, that means you need to apply more effort than load. It shows that more effort is required to lift smaller load. That means it does not provide mechanical advantage. Once again, if it does not provide any mechanical advantage, why do we use this kind of machine? Some of the examples of third class lever is a shovel. In a shovel, this is a shovel, yes. Load is applied here. Okay, you anchor shovel over here with your left hand, and you apply effort over here to lift the load by using your right hand. Okay, effort lies between fulcrum and load. Shovel is a kind of third class lever. Why do we use it if it does not provide mechanical advantage? Well, yet it makes our work faster. Why? Why does it make our work faster? Because effort has to cover less distance than load. Okay, effort has to cover less distance than load. And the question from this part of your lesson is, although third class lever does not provide mechanical advantage, why do we use it? Why is it used often? Okay, got the question? Okay, write it down. Although third class lever does not provide any mechanical advantage, why do we use it? Okay, this should be the answer. Pause the screen, copy it. Okay, or you can also be asked what advantages can be gained from third class lever. Okay, so what advantages can you gain? Advantages from this derivation, we can see that it does not magnify our force, yes, but it makes our work faster. Okay, this is the main advantage provided by it, and it does not change direction of force as well. Only first class lever does that. However, it also transfer force from one point to another. Okay, this much is from the lesson lever. Okay, now we are going to discuss some numericals. Okay, but before doing numerical, you need to take out some formula. Okay, for lever, mechanical advantage is equals to load by effort. This remains same for all, whereas velocity ratio equals to, it is effort distance by load distance. Yes, it is effort distance by E, capital D, capital L, capital D, and it's effort distance by load distance. But as I told you, effort distance by load distance is proportional to effort arm by load arm. Do you remember in which paper, let me show. Okay, here we have said it. Yes, effort distance. Okay, effort distance and effort arm are not same. Load distance and load arm are not same, but the ratio of effort arm and load arm is equal to effort distance and load distance. Okay, that's why the actual formula of VR is effort distance and load distance, but we can replace the whole ratio as effort arm by load arm. Okay, that's how we get this formula. Therefore VR is equals to E small d by L small d, effort arm by load arm. Okay, or effort arm by load arm. Okay, this was is the formula you need to take out. And similarly, sometimes efficiency equals to MA by VR into 100%. This also is needed. And sometimes you might be asked to find out input work and output work as well. Okay, output work. In that case, input work means effort into effort distance, and output work is load into load distance. Once again, here also either you can use effort distance or effort arm. Okay, here also you can use load distance or load arm, but that will not give you exact by using effort arm. It does not give you exact value of input work. Okay, to calculate input work you need effort distance, but it also, by using effort arm also, it gives you exact value of efficiency. Okay, when you calculate input work and output work from here and use the formula of efficiency as output work by input work into 100%. Okay, so how many formulas are there? 1, 2, 3, 4, 5, 6. Okay, these 6 formulas you will need to perform numericals. Now I will give you some questions on numerical and for your homework. Let me pause the screen until I take copy the question. Then you also need to pause the screen and take out the question. Okay, I have collected some question. First of all, these 5 questions you need to justify by using the method I showed earlier. Okay, by using principle of simple machine, like this one. Okay, so the questions are: question number 1, differentiate between second class and third class lever. This is simple differentiation question. You need to use the table. Second, justify that second class lever magnifies effort. We have done this. Justify that third class lever does not magnify effort. It's also we have done. Okay, what happens when fulcrum is shifted toward load in a first class lever? We have done. What happens when fulcrum is shifted toward effort in a first class lever? Okay, first toward load, second toward effort. It's also we have done. Numerical, look at the figure. Okay, you need to calculate MA, VR and efficiency, and don't be confused here. Load arm is 20 centimeter, convert it into meter. Again, there is no problem. And effort arm, you tend to write 60 centimeter. Yes, effort arm is 60 centimeter. No, effort arm means distance from effort to fulcrum, that is 20 plus 60, it would be 80 centimeter. Okay, don't make that mistake. And second question, a block of 800 Newton is raised through a vertical distance of 6 centimeter by using a first class lever whose velocity ratio is 10. Given that efficiency of the machine is 80%, draw the diagram of lever, calculate MA, calculate effort. Okay, this is also easy. Once you draw the diagram, it won't be difficult. Like draw a first class lever. The question says first class lever, isn't it? And then load is here 800 Newton, but you don't know effort. How much effort you don't know. Yes, but you are given load distance L, capital D, load distance 6 centimeter you are given, and you are given VR is given 10 and efficiency is given 80%. Now by using these two information, first of all, okay, by using this information, first of all you need to calculate MA, and after you calculate MA, you have load, isn't it? You have load means by using formula of MA equals to, okay, here you can use MA by VR into 100%. Okay, by using this formula you can calculate MA, and then by using formula of MA you can calculate E. Yes, and you can calculate effort from here. Okay, anyway, all the best with those numericals. At the end of lesson I'll give you more questions to practice. This much for today. Thank you.